Imagine it's Black Friday. Your marketing team is running a $1 million ad campaign, but the dashboard they're looking at is showing data from 6 hours ago. By the time they realize a campaign is failing, the budget is already gone. Or imagine a fraud detection system that flags a stolen credit card after the transaction has cleared. In modern data engineering, slow isn't just a technical lag, it's a business failure. But here's the problem. Making data move faster usually means breaking something else. If you want it now, you often sacrifice accuracy, structure, or cost. This is the central conflict of the right path, the war between data latency and system stability. In our last discussion, we defined the difference between data latency, how fresh the data is, and query latency, how fast the dashboard loads. Today, we are zooming in on data latency. We're going to look at exactly why data gets stuck in the pipes and how our architectural choices, from staging layers to the batch versus streaming debate, determine whether your company is making decisions based on the present or the past. Specifically, we'll look at why data latency exists in the first place, how ingestion pipeline design affects it, why staging layers are both your best friend and your biggest bottleneck, and the high-stakes trade-offs you make when you finally flip the switch from batch to streaming. Think of this video as focusing on the right path, how data moves from the source into your analytical system. First, let's look at why data latency exists in the first place. Data latency is driven by one simple question. How long does it take for data to move from where it's created to where it can be analyzed? The delay is influenced by every step in the ingestion pipeline. The more steps data has to go through, and the more work each step does, the higher the data latency. So to reduce latency, we have 3 broad strategies. Simplify the ingestion pipeline, reduce the number of intermediate staging layers, shift from batch processing to streaming. Let's walk through each one, focusing on the ingestion pipeline first. The first way to reduce data latency is to simplify what happens to the data before it lands in its final destination. A major contributor to latency is data transformation. What is data transformation? Data transformation is the process of cleaning raw data, fixing errors, formatting values consistently, enforcing business rules, and reshaping data to match a target schema. This work is often necessary, but it's also expensive in terms of time and compute. But why does cleaning and formatting take time? It's because raw data is messy. When data is extracted from different sources like SQL databases, Salesforce, and spreadsheets, it often contains issues such as duplicate records, missing or null values, invalid values like transaction dates in the future, or inconsistent formats such as phone numbers or timestamps. So we write code to clean it by deduplicating identical records, deciding how to handle missing values, and filtering or flagging values that don't fall within logical ranges. After cleaning the code, we would format it. For example, convert text like this into a proper date type, standardize phone numbers into a single pattern, and ensure consistent units and representations. Finally, we reshape it to fit the destination schema. For example, combining first name and last name into full name, renaming fields, or enforcing required columns and data types. All of this takes time, and the more rules you enforce, the longer transformation is going to take. This brings us back to an important design trade-off. The more structure you enforce up front, the higher your data latency. Highly structured pipelines act like gatekeepers. If incoming data doesn't match the rules, it gets rejected or sent for reprocessing. That increases reliability, but it also slows down ingestion. On top of that, highly structured pipelines tend to be brittle. A small change upstream, for example, marketing adding a new TikTok ID field, can break the pipeline and require code changes before data can flow again. That's why one way to reduce data latency is simply to reduce transformation complexity, especially early in the pipeline. Let's move on to the second strategy to reduce data latency: reducing staging layers. As mentioned previously, another contributor to data latency is the number of staging layers data passes through. A staging layer is an intermediate storage location used during ingestion. Instead of loading data directly from the source system into the data warehouse, we often extract data from the source, write it to a staging area, then transform and load it into final tables. Staging layers exist for good reasons. They protect the operational database from long-running queries. They provide a raw historical copy of the data, and they make debugging and recovery easier if transformations fail. Once data is copied into staging, the connection to the source database can be terminated quickly, minimizing impact on transactional workload. However, every staging layer is another stop in the pipeline. More stops mean more input-output overhead, more processing, and more coordination, which eventually mean higher data latency. So if your primary goal is freshness, one way to reduce data latency is to minimize the number of staging layers or delay staging and heavy transformation until later. But this also comes with a trade-off. When you remove staging layers, you're trading safety and the ability to debug for speed. That decision has to be made carefully based on how critical freshness is compared to reliability and auditability. Finally, let's look at the last strategy to reduce data latency: shifting from batch to streaming architecture. This is the most powerful way to reduce data latency. In a batch architecture, ingestion is driven by a scheduler. A tool like a cron job or Apache Airflow wakes up at a predefined time and runs a job. Until that job runs, data just sits in the source system. For example, a transaction happens at 9 a.m. The batch job runs at 2 a.m. the next day. The data is invisible to analytics for 17 hours. The system is idle, not because it can't process the data, but because it's waiting for the schedule. Streaming systems flips this model completely. Instead of waiting for a scheduler, the data itself becomes the trigger. As soon as a record is created, it's pushed into a message bus or event queue. Systems like Apache Kafka acts as high-throughput buffers, and downstream consumers continuously read from this stream. The pipeline is always running. Data flows continuously instead of in large chunks, and transformation happens on small batches or individual events. A continuous service reads records from the queue, applies light cleaning or validation, and inserts them into analytical storage immediately. This reduces data latency from hours to seconds or even milliseconds. At this point, streaming might sound like the perfect solution to optimize data latency. However, it comes at a cost. When data arrives continuously and in raw or lightly processed form, there is less opportunity to pre-aggregate or reorganize data, as the goal is to get the data to the final destination as quickly as possible. Therefore, the queries often have to compute results on the fly, taking the dashboard more time to finish loading. So while the data is extremely fresh, query latency often increases. Streaming systems also introduce more complexity as it requires always-on services, stateful processing, ordering duplication, and retry logic. This is why streaming is typically used only when low data latency is absolutely required. So in this video, we saw how data engineers reduce data latency by simplifying ingestion pipelines, reducing staging layers, and even shifting from batch to streaming architecture. But here is the catch. We just made our data super fast, but we might have made our queries incredibly expensive. Speed on the write path often kills performance on the read path. In the next video, I'm going to show you how to solve that equation without bankrupting your budget. If you found this helpful, like and subscribe so you don't miss the next part of the series. See you next time.